So examples of measurements, these include mass, volume, time, length, width, I believe I spelled that right, and height. And these three, length, width, height, these are what you would call measurements of distance. So yeah, these are your examples of measurements. Most you'll encounter them a lot as you go on in chemistry, general chemistry, yeah, stuff like that. Can't really think at the top of my head if you're gonna see this in organic, but you probably will. Measurements and stuff. Okay, so let's continue. So measurements have units, right? They are used to quantify a physical property. So basically, you just take something from the real world, and you use units. You use measurements, or you measure it using either like tools like a ruler, a scale, stuff like that to give it a number of quantitative quality to it. So like a value to it, right? We want to quantify a physical property. So let's look at an example. The example here is how long is this spider in centimeters? So let's go ahead and draw this stuff. So assume we have a ruler. Let me draw it in, okay, let me do it in this color, in black. So assume we have a ruler, right? So this is going to be your ruler. And we're going to measure in centimeters. So let's just say this is 0 centimeters. This is probably not what a real ruler would look like, but this is just to get a point across. So that's 0 centimeters. This is 1 centimeter. And then this is 2 centimeters, right? And let's put like a dash or a line in between them to represent that, the halfway mark between the each of the whole centimeters, right? So let's go ahead and draw a spider, or any type of insect you guys want. Let's go ahead and draw a spider. Doesn't have to be perfect, but just pretend we found a spider in the lab, and we want to measure it. So actually, let's make it a black widow spider. Actually, that's in there under this thing. The red stuff is probably under underbelly, rather than on the top of them. I think I'm not that sure, but I think that is on top, like under in their underbelly. Sorry, on their underbelly. So this spider is probably just on its back, with its red part towards us. So just for the fun of it, let's make it a black widow. So we found the black widow in lab, and that is probably not really a good sign. So but that's okay. So let's go ahead and draw, and the black widow's legs are probably not this long, but just for the purposes of our demonstration right here. Yeah, this is a horrible spider, but this is just to get the idea. And typically its front legs are probably going to be longer than its back. So this is just a really inaccurate drawing of a spider, so just, it's okay. It's okay. We're not biologists here. We're chemists. Okay, so example. So how long is this spider in centimeters, right? So let's just say, okay, how long is it? Well, let's see. It starts at 0, or it looks like it starts at 0, or close to 0. And it ends at somewhere where it looks like it's close to, or maybe around the halfway point. So we're gonna say, this is just what we're gonna say. We're gonna say it's 1.5 centimeters long, right? This is gonna be a unit. This here, your centimeters, this is a unit. So this is a unit. That's gonna be your unit. So what we did here is that we took the bug's length, we took the spider's length, how long it is, right? Measure of distance. We took how long it is and assign a quantity to it. So we assign a numerical value of 1.5 to it. right? So that is what we did. And basically what I want to get at this is that, remember when I drew these like dotted lines right here and I said oops, and I said, oh, it's probably around this and that. So we don't know if it actually, like, is lands perfectly between these boundaries, these dotted lines that we drew. We don't know that for a fact, right? We're not 100% sure. But what we do know is that it's bigger than 1 centimeter, right? It's bigger than that. That is what we're certain. That is what this ruler is certain about. So it's bigger than 1 centimeter. So let me go ahead and write this down. So we are certain that this line reads 1 centimeter. That's what we're certain. 1 centimeter. That it reads that, right? But we are allowed one more decimal place of uncertainty. So basically an estimate, right? So again, going back to this 1.5 that we said, 1.5 centimeters. This right here, that is an estimate that we are allowed to do. So let's just call that 5 an estimate. And we are certain about the 1. So this is certain. We know that. The ruler says that 1 is certain, right? That's your certain value. So we know that the spider clearly passes 1, but we're not so sure whether it actually lands on the 5, right? So if this spider was perfectly aligned, if this spider was like perfectly aligned to the line, the dotted line, we still wouldn't really, like, just imagine us shifting the spider until it's perfectly aligned to the 0, like theoretically perfectly aligned, and still measure it. Are we 100% certain that the spider is going to, like, let's say, pass, or where exactly, like right here, will it land, right? Will it land on 1.4 or 1.5 or 1.3? We know about this. That's certain. But we don't know about these. We don't know about them, right? So since we don't know about those that's going to be your uncertainty. We don't actually know, like, we're not 100% sure about that, right? So that is what we call an estimate. So this is the estimate that we are allowed. The estimate you guys are allowed are basically going to depend on the ruler, right? So in this case, the ruler is only certain to this place. This, it's uncertain. We don't know about that. So the ruler, we'll see later on, a different ruler that will let us estimate another digit right here, so we can actually write 3 digits instead of like 1. But we'll see that later. If it's not clear, then just ask me and I'll hopefully be able to clarify some stuff. So let us move on. So units like centimeters, inches, meters, kilometers, etc., all the units you guys are going to see throughout chemistry and some physics are fixed, right? They're fixed. They don't change. So fixed means that they don't change, right? They're fixed. Pretty much people from around the world would agree that a centimeter is a certain amount of length, and so on and so forth. Like a centimeter is 2.54 inches. An inches is 12 feet. 12 inches is a foot. A centimeter is 2.54 inches. Did I say that? No, I meant 2.54 inches, a centimeter. No, 2.54 centimeters is in an inch. I'm sorry about that. 2.54 centimeters is in 1 inch. Okay, so that is what people are going to agree on, right? Everywhere. And that 12 inches aren't a foot. We are going to agree on that everywhere in the globe. So that's what we mean that they're fixed, right? So they don't change. These things don't change. So yeah, basically, we use them to quantify physical properties. And we can agree on these units. And we'll see more about this stuff like in like calculations and whatnot. So yeah, we can agree on these units. So let us move on. So we have a comparison here to do. This is I'm gonna compare what I said right here, this last thing, to the where it says compare. So we're just gonna compare these. We're just gonna see this statement in action. So yeah, basically compare. So basically this is just saying that assume that if we measure a cat from its head to its toe, so like yeah, you got like a cat or something. I can't draw a cat. You got a cat right here. If we measure from its head to its toe, I'm not really 100% sure about these measurements, if this is how big a cat actually is. I literally just made stuff up, but that doesn't matter. What matters is us seeing that units are actually fixed. So that doesn't matter. A cat can possibly be 3.5 oranges tall. I mean, it seems likely, but we're not like zoologists or whatever. So let's go ahead and continue. So let's compare. The cat is 3.5 oranges tall versus the cat is 12.5 inches tall. Remember what we said, that inches is a measurement? Is that how you spell it? Measurement. Close enough. Okay. So apples vary in size. Oranges. Oranges vary in size. Right? You can have you can have like an orange like this. Looks like a cookie, but it's an orange. You can have an orange like that. Oranges vary in size. They're not fixed, right? So this is not a measurement. You go to the vet. The vet tells you, "Oh, your cat is 3.5 oranges tall." You're like, "Yeah. Are they large oranges? Are they medium oranges? Are they small oranges? What kind of oranges are they?" Like, you go to the store, you see all these oranges of different sizes. They're not fixed. They cannot be used as measurements. So for us here in introductory chemistry, we're not going to use oranges as measurements. They're not measurements. Yeah, probably measurements for someone else, but for us, for this purpose, they're not going to be measurements. But the cat is 12.5 inches tall. So inches don't vary, right? Inches don't vary. So they are a measurement. They are a measurement. Measurement. The inches are a measurement, right? Like I said before, an inch, 2.54 centimeters is in 1 inch, and that's not gonna change. Go to Canada, go to like England or someplace, it's gonna be the same. 2.54 centimeters is gonna be in an inch, and that is agreed upon. So these are not gonna change. Therefore, they are a reliable measurement, right? So, okay, so this is basically just assuming. We'll talk about this later on in the lecture, I think. This is basically just assuming. Assume we are exact and no experimental error. Like, let's say you go to like take your cat to the vet. They measure it. They probably measure it in centimeters. I'm not really sure. I don't even know if we measure cats in the vet, like their height. But let's just assume that we do. You measure them, like the vet measures it. Okay. Oh, I'm not gonna convert inches to centimeters in my head, so I'm just gonna stick to inches. Oh, 12.5 inches. 12.50 inches. You go to another vet. Oh no, it's 12.51 inches. That is what's going to be experimental error. Like the measuring of the same quantity, aka the cat's height, the same physical quantity, gives us like different measurements, right? 12.5, 12.51, 12.501. All of these different measurements for the same physical quality or same physical property, which is the cat's height. That is going to be your little error, your human error. So assume that we don't have any error here in this example that we just went into. So assume that there is no error and that the cat that was measured with oranges is exactly 3.5 oranges tall, and the cat that was measured in inches is exactly 12.5 inches tall. No experimental error. Just assume. This is probably impossible, but just assume. Just assume for the purposes of our perfect world here. So yeah. So yeah, just to get straight to the point, oranges are not a measurement, but inches are a measurement. Let's continue. This is exactly what we were talking about, the experimental error. Experimental error in measurements. You get slightly different measurements for the same physical quantity, right? Basically what we just spoke about. So I don't think I want to skip this. Let's go over it again because I don't want to skip it. I do not want to leave these notes blank. So example, mass of a sample, right? So mass of a sample, let us say that one student measures, where's my pen? Okay. One student measures 3.23 grams. You measure 3.24 grams. Your lab partner measures 3.22 grams. So basically this is what we would call experimental error. Experimental error. So yeah, and remember, experimental error, why we have this is because remember our estimate, right? The last digit would typically be your estimate. So since the last digit here is will typically be your estimate, these two digits in front, those are going to be your exact. And remember, the ones underlined are your estimate. Remember that. So remember, we are allowed, well, in this case, in this set of data, we are basically allowed another decimal points to the, what is that, the hundredths place? I believe that's the hundredths place. So we are allowed an estimate to the hundredths place. That is why you estimated, oh, it's 3.24 grams. That is why your lab partner estimated, no, it's 3.22 grams. That is why that other student, who's not your lab partner, I don't know why they're talking to you, said, no, it's 3.23 grams. 3, 4, and 2, those last digits of every measurement is going to be your estimate, right? Because you are allowed an estimate. Typically, in every single measurement you're going to be making in chemistry, in introductory chemistry, general chemistry, that stuff, they're gonna have a estimate at the end. Like the last digit is gonna be the estimate. You cannot have 3.233. If we are measuring with the same tool, and like I said before, this is your estimate, you cannot have another estimate to, like, what is that, the thousandths place? You can't have another estimate if you're only allowed an estimate to the hundredths place, like we are here in this set of data. So no, that is not allowed. Not allowed. Don't do that. We're only allowed one estimate, right? Don't do two, don't do three, just one estimate. That is your uncertainty. That is what you are allowed. That is your estimate. Okay? So if you guys are measuring like with a tool like we are doing here that only goes up to three sig figs, like let's say it's one of these scales that look like that, right? Like you put stuff here, weigh stuff here. Say it's one of those scales that look like that. That's a horrible drawing, but like a scale you see at like a grocery store. Let's say it's one of those scales. You are allowed a one decimal place estimate here, right? Okay, let us move on. Wait, is that all I wanted to talk about here? Yeah, it looks like it. Okay. Let's move on to some significant figures. Significant figures, we also call them sig figs. So they're a number from either a measurement or a calculation, right? So either you measure something like we did, like with the spider, with the stuff over here, measuring stuff on a scale with the grams and stuff, that stuff. Those are going to be your measurements. Calculations, we're going to go over calculating stuff probably in the next lecture. So that we can also get significant figures from a calculation, and we can also get significant figures from a measurement, right? So let's see. So they have, right? Let's go back to our, it's basically what I explained in like earlier, but let's go back to the whole spider measurement, which was 1.5 centimeters. And like basically like I said, basically just recapping. This is your uncertainty. This is your estimate. Right? And this is what you are certain about. You are certain that you are at one. Or, I mean, you are passing one, right? You are certain about that. So, assuming we go back to the whole spider measurement. Okay, yeah. So, assuming we go back to the whole spider measurement. If you, and assuming you have the same ruler, so assume same ruler. If you measure 1.50 centimeters, so if you measure that, if you say, oh, it is 1.50 centimeters using the exact same ruler, using the exact same spider, is that correct or incorrect? We did go over this right here. Right here, we went over it. Using that common sense or whatever it's called, we can say that that is actually incorrect, right? That is incorrect, right? So no. Let's say, yeah, no. Our ruler only allows for an estimate at the hundredths, at the tenths place. Sorry, not the hundredths, at the tenths place. So, like I said before, this is your estimate. Are you allowed this one? No, you are not allowed that one. Because you already made an estimate. 5 is your estimate. You cannot go another estimate. No 2 estimates, only 1 estimate, right? Remember our ruler. Centimeters. This is, let's say 1. This is 2. And we have the halfway point. This is your spider. Yeah, whatever. Just its 2 front legs. And then we're just gonna assume like it goes all the way to like 1 centimeter. I mean, like the 0 right here. What happened? Whatever. Let's continue. Okay. So remember your ruler, right? We are certain about 1. This, we are certain. 1. Certain. I hope you can see that. I mean, read that. It's too big. Certain. Right? We are certain about 1 because a spider obviously clearly passes 1. But we are not certain about if the spider crosses the 0.5 mark or not. We're not certain about that. Like, if we're like, oh, does it? Well, I don't really know. We're not certain about that, right? So 0.5, like I said, that is your estimate. Your 0.5, the 5 here that I underlined, is your estimate. You cannot have another estimate, so that is incorrect. No, if you have a ruler like that, don't report your measurement like that. That is false. You're basically saying, oh, I'm sure about that 5. You're not sure about that 5. So don't report the 5, right? But what if, using the exact same ruler, let's draw the exact same ruler again, right? This is your 1, this is measured in centimeters, 2, and this is your halfway point, right? So this is just zoomed in of the same ruler. So let's say your spider lands here. Let's say, what if your spider length is here? Right here. What if you measure the spider here, right? We can say it is 1 point, I don't know, just make something up. 1.6? Nah. Say it's 1 point, I don't know. Say it's 1.8 or something. Nah. There. Let's say it's 1.7. Right there. It's really bad to look at. That was a horrible place to land. But that doesn't matter. I'm here to like tell you that's not the point. Okay. So what if it lands there? We can say it's 1.6. Someone else can say it's 1.8. Someone else can say 1.7 or whatever, whatever it is, right? Somebody can say that, but it's clearly past the 5. But then again, we are past the 5, right? But this is still going to be your estimate. This is still an estimate. I want to read. Still an estimate. That is still going to be your estimate because we are certain. Because like we are certain that yeah, sure, it is 1 and we did pass the halfway point. But we landed somewhere where we're not like really like, we don't know, right? We don't know where we're at. So that is why 7 is still going to be your estimate. Because you don't know where you're at. You don't know whether you're halfway between like 7 and 8 or whatever. We don't know where we're at. So that is why 7 is still your estimate. And that is why you are going to report your measurement how I wrote here with 2 digits, 2 significant figures, right? So there's two significant figures. Two sig figs. Again, if it's not making any sense, please let me know so I can clarify. So yeah, like I said before, just before we move on, this is your estimate. Why? Because we are not 100% certain of where exactly the spider lands, but we are certain that it passes the 1 and the halfway point, right? But we're not certain exactly where it lands. So that is why we still have that decimal place, that estimate in the tenths place, right? It obviously wouldn't make any sense if you said, "Oh, the spider is 1.3 centimeters long." That's obviously, I mean, common sense. That won't make any sense because like we're obviously past the halfway point, so that won't make sense, right? No sense. That's just, I mean, I guess that's just like common sense or something. So that 1.3, you're like, oh, that's 1.3. No, that doesn't make any sense. So just take into account that it did pass the 0.5. What if okay, what if we have another ruler? Let's draw this other ruler. There's gonna be probably like a horrible drawing, but I hope I can draw well. So what if we have another ruler, again in centimeters? And we have, got your 1 right here. You got your 2 right here. And let's say you got your 1.5 right here. And then we have 1, 2, 3, 4. 1, 2, 3, 4. So it's 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 2. 2 centimeters, right? So what if we have this ruler now? And what if our spider lands, let's see here. What if our spider, the length of our spider lands here? Right here. Okay, so now we are certain. What are we certain? We are certain the length of the spider is past the, well, what is going on here? Is past the 1.5 mark. We are certain about that, right? So what does that mean? Like I said, we are certain about these two. We are certain. And what are we allowed? We are allowed one estimate. Remember that we are allowed one estimate. So we can report our findings as maybe 1.5. Let's estimate between the 0.5 and the 0.6. It's going to be your point. So that's going to be your 0.5, and that's going to be your right here. That's going to be your 0 to 1.6. So it's between those two values. So just like to zoom in, we're right here. We're in 1.5, and there's 1.6. So basically just zoomed in. This is where we're at. So we are allowed to estimate right here. So estimate. But we are certain. We are certain we are over 1.5. We are certain about that. So this won't change. We know that it's 1.5 regardless. It's always going to be 1.5. Your lab partner is probably going to see 1.5 something, or you will see 1.5 something, your professor will see 1.5 something, but what is here, that is what you are allowed to estimate, since we know that it's 1.5 with this ruler as compared to this ruler here. We already went over that. we know that it's 1.5, and we are allowed one extra decimal place of uncertainty, one extra estimate. We can estimate. I'm gonna estimate this as 1.52, and this is your estimate, and that is what you would call three significant figures, three sig figs, right? So we are allowed this guess. We are allowed the 1.52. 1.5 is certain. No one can disagree with what I wrote here, that the spider does cross the 1.5 mark. So it is certain that the spider is bigger than 1.5. No one can disagree about that. But your partner, your professor may disagree. Oh, it's 1.53. No, it's 1.52. No, it's 1.51. They can disagree on that. That's fine. And that is why that is your uncertainty. So you are allowed an uncertainty. And in this case, I am going to say that is 1.52. It might be slightly off, but we are allowed to make that uncertainty, right? So yeah, just keep that in mind. Obviously this won't make any sense. The 2 won't make any sense if you're like all the way over here. Then yeah, obviously maybe don't choose 2. But just try and keep it within like the same, like an educated estimate, right? Try and keep it as an educated estimate. So yeah, if you see the dot, like the spider end up right here, not passing the 1.6, don't say it's 1.51, 1.52, because it obviously doesn't make any sense. Just make an educated guess about it. That's it. Let's see what else. So yeah, basically what I said, that the 2 in the 1.52 is going to be your uncertainty, and this ruler basically just allows the uncertainty to the hundredths place, like I what do you call it, I explained. Let's move on. Significant figures, what do they mean, right? So what we've been talking about significant figures, but what exactly do they mean in this case? So they basically, they indicate the level of precision, however you say it, precision. So they indicate the level of precision in a measurement or calculated value. So they measure how like precise, how how precise these measurements are, or these calculated values are. So the precision, let us say that the precision is how close our measurement, or our measurements, a set of measurements are to each other. So an example would be 1.51 grams, right? 1.52 grams, 1.50 grams. So if you keep getting measurements around those values, you can say you are precise. Your device is calibrated correctly, and you are precise in your measurements. So it's basically how close these values are to each other. That is precision. There's accuracy, but we're not going to go over that. That's for another lecture. But right now, precision is how close your values are to each other. So yeah, if you keep getting values that are super close to each other, kind of like we wrote here, 1.51, 1.52, stuff like that, then you are precise. So they indicate basically the level of precision in a measurement or calculated value. Basically it. So So yeah, they're just used to see, oh, how precise are my measurements? That's all they're used to. That's what they're basically used for in lab. How precise are my measurements? How precise are my calculations, right? That, so we'll see more about that in calculations. It'll probably make more sense in calculations. Okay, example. Consider a scale for weighing food, right? Like a kitchen scale. Like let's say you want to like track your macros. You want to know how much protein you're getting, how much calories, how much uh, carbohydrates, all that good stuff. So consider a scale for weighing food. If 4.2 ounces of chicken contains 25 grams of protein, what numbers will be significant to you on a scale? So, in other words, what do you care about? Like for you, let's say you gym bros or some people out there who are like really into their macros and stuff like that. What do you care about? Just ask yourself that question. Just pretend you're like you're super strict on your diet. You really want to know what like what you're eating, what you're consuming, protein, all that good stuff. You really want to know that, and you start weighing your food. What do you care about? Let's see. For this example, let us draw there's going to be an ugly looking scale, but doesn't matter. So this is going to be your scale. And let's say this is like your plate that you like put to measure stuff in. And let's say it's already like you already put your chicken in there. And the scale reads this is what your scale reads. So just, and this is in ounces, by the way. Ounces. So assume your scale reads 4.27 ounces, right? With the 2 zeros in front. So basically, what I'm getting at, what numbers will be significant to you on the scale? What do you care about? These 2 zeros, right? Let's draw a line or an arrow. Do we care what's in front? Do we care about what's in front? Like, do you care if you were to like track your macros, track your diet, your dietary stuff? If you were to measure out 4.27 grams of chicken, do you care about those 2 zeros in front? Like, do you care about them at all? Like, would it make a difference to you if they weren't there? No, you just want your 4.2 ounces, right? So no, we don't care about that, right? So this is what we would call insignificant. They don't mean anything. They're insignificant to us. Oops, what did I do? Sorry about that. So, insignificant. Those are insignificant. We don't care about those number zeros here, right? How about here? The 4 and the 2 and the 7. Do we care about that? Yes. Yes, we do care. So this is significant. That is significant. We do care about the 4.27 grams, right? So this is what you would, and this is a measured value, by the way. So yes, this is what we would say it's 3 sig figs. 3 significant figures. 3 figures that actually mean something. They mean something to you, right? We don't care about those 2 zeros in front. They don't mean anything to you. They're insignificant. Those are not significant figures. But we do care about the 4.27 ounces. We do care about that. Those do mean something to you. So they are significant. That is what we mean by significant figures. So we do care about those final digits. If we want a value closer to 4.2 grams, right, for our dietary needs, then the 7 and the hundredths place matters. And if we want to get closer to the 4.2 ounces of chicken, we want to like stick to our diet. You don't really want to go over the 4.2 ounces. So that 7 over there is basically saying, oh, you're actually closer to 4.3 ounces, but you only want 4.2 ounces. So that 7 does matter. So you are going to lower it. So that is why, like, we care, right? And let us continue. So here are some significant figure rules, some rules for sig figs. So number 1, all non-zero digits are significant, right? So all non-zero digits are significant, kind of like we saw in the previous example. So we have, for example, we have 213 centimeters, 1.76 centimeters, 1.327 kilograms. So look at all of these are non-zero numbers. And like I said, all non-zero digits are significant. So this is 3 sig figs. 3 numbers that actually mean something. And this is 4 sig figs. 4 numbers that actually mean something. 4 sig figs. Let's go ahead and continue. Zeros in front of the quantity are insignificant. Zeros in front of the quantity are not significant, right? Again, let's look at an example. 0.000021 kilograms. And then we have 0.00073 pounds. These here are insignificant. Insignificant, right? Kind of like the example that we went over with the scale and the chicken. So those are insignificant. So that means that these two are actually 2 sig figs, right? 1, 2. Same with the other one. 1, 2. 2 sig figs. Let's go on to number 3. So all zeros on the right side of the decimal place, they are significant, right? So yeah, we're at number 3. So all zeros on the right side of the decimal place are significant. So we have 0.002100 meters. And then we have 2.100 kilograms. And then we have 2.70000. Okay, going back to our rule number 2, that the zeros in front of the quantity are not significant. That means that these are not significant. So don't count those. But the zeros that follow, like on the right side, on your right-hand side, those are significant. These are significant. They mean something, right? So if your scale said, oh, it is 0.002101, you do care about this, right? What if it said, it's this? You care about that. So you want to... That is why they're significant, because you actually care about that. Let's say you're... I know it says meters, but just pretend that it's like you're weighing it on a scale and it's grams. Just pretend it's grams for now. Say, oh yeah, like, we do care about that. We do care about what this last digit says. So that is why it's significant. So this here, same with here. Let's say, I don't know. Let's say a rope can only carry 2.100 kilograms. That is its max. Just an example. If it read 2.101, the rope will break. Do you care about that one? Yes, you do care about that one. You want your weight to be no more than this. That is why we care about that. So it is significant, right? So these two, they're 4 sig figs. And we already went over this. So therefore, using our knowledge, we can say that this here is 6 sig figs. 6 sig figs. Right? So yeah, just like our scale example, we do care if the scale reads 4.20 ounces or 4.22 ounces. Like we care about that stuff, right? And they mean something. Therefore, they are significant. Number 4, decimal points can help. Yeah, sure. Decimal points can help make values significant. If we don't have a decimal point and the significant figures are not given to us, then we do not know how many sig figs there are, right? So we don't know about that stuff. So let's look at an example. Example is let's say 200 kilograms versus 200 point kilograms. You got a decimal point. You got a decimal place. So this here is what we would call ambiguous. How do you spell it? I believe that's how you spell it. I don't really know. Ambiguous. We don't know. But here we have 3 sig figs. We do know. Because we are given a decimal place. So notice the decimal point. In the 200, in the example that says 200 kilograms, that's ambiguous. It does not have a decimal place. And we are not given the sig figs. So we don't know how many sig figs they are. That value has. But in the 200 point kilograms, we are given sig figs. We are given sig figs, sorry. We are given a decimal place. And the decimal place tells us that we are certain, that we have that many sig figs, 3. If we had another, let's say for example, 200.0, using your previous the previous step, what is it going to be? How many sig figs? 4, right? 4 sig figs. Using step 3. Or rule number 3, sorry. Rule number 3. Right? So yeah, just notice a decimal point. So yeah, basically, we'll talk about scientific notation later on. So scientific notation can help get rid of the ambiguity, right? So, but this will work if you're given the sig figs. Like, for example, this one. We are technically given the sig figs because we are given the decimal point. So we're going to go over scientific notation very briefly, and then in the next lecture we're going to go over all this stuff, calculations and all that stuff to more depth. So just an FYI, this can be written as 2.00 times 10 to the what? 10 to the 2. That is going to be your scientific notation. That looks weird. That's going to be your scientific notation, right? So this here is going to be your sig figs. And we have 3. 3 sig figs. So anything you put here, anything at all, is the amount of sig figs. Let's say, it is 2.000 times 10 to the 2. That's 4 sig figs. right? So whatever you put there, that's going to be your sig figs, except for the 0, right? You don't count that. So just remember your rules and you'll be fine. About the rules, yeah, I remember them, but it's not something you have to spend like hours just memorizing these rules. Just do a bunch of problems and they'll eventually come to you. Don't just sit there and make flashcards about these rules. Like, maybe it can help, maybe, but don't spend so much time on trying to memorize sentence per sentence. No, just actually start applying these rules, and they'll come to you. So scientific notation. It is in the form of n times 10 to the, well, uppercase n times 10 to the lowercase n. So this here is going to be your integer, your integer or whole number. And this is gonna have your precise sig figs. Like we went over there, right, in those examples. So that's just going to be your scientific notation. Again, more on this in another lecture. I feel like I'm going long enough for the introduction. So let's look at a few examples. Oh, almost done, hopefully. Write 273 million in scientific notation and assume we have 3 significant figures. So we are given the sig figs. So we're going to have to write this in 3 sig figs. We're not given a decimal point, but we are given the sig figs. So we can write this in scientific notation. So we have 273 million. So in order to do this, you want to start here. Just imagine a decimal place right there. And you're going to want to count 1, 2, 3, 4, 5, 6, 7, 8. And you're going to basically want to write it in this format. You want like a 2.73. We'll see. We'll see later on. Hold on. 2.73 times 10. This is going to be your n, right? And then we're going to have a little n. What's that little n going to be? Well, that's easy. Just count the number of places your decimal place basically hopped. So 1, 2, 3, 4, 5, 6, 7, 8. 8 places. So yeah, this is 3 sig figs. 1, 2, 3. And you're gonna write it like that, right? But there is technically another correct way. Well, there's many correct ways to write this, but there's another correct way to write this. But we're not gonna do it in chemistry because it's correct, but maybe your professor might not want it this way. Let's start here. 1, 2, 3, 4, 5, 6, 7. Let's stop at 7. 7.3 times 10 to the, we hop 7 places, 7. So these are equal. They're equal, right? But you want to write it like this. So write it like that. But they're the same. 2.7.3 times 10 to the 7 power is the same as 2.73 times 10 to the 8 power. And look, 3 sig figs. So write it like this. Even though this one is technically correct. But chances are you're not going to see it like that. So yeah, 7 jumps, 10 to the 7 power. 8 jumps, 10 to the 8 power, right? Let's go ahead and continue some more. Example, write 0.00000713 in scientific notation. Remember our sig fig rules. How many sig figs do we have here? 3. So our scientific notation like form needs to have 3 sig figs if we are given 3 sig figs, right? So yeah, let's do this. 0.0000713 in scientific notation. You're already given a decimal place, so start where the decimal place is at. And again, we want it in this format, so just keep that in mind. Let's go ahead and do it. 1, 2, 3, 4, 5. 7.13 times 10 to the negative 5, right? Because this time we're moving to the right. And this time we're moving right, like right here. In our previous example, we moved left. Same here, left. So our answer is going to be 7.13 times 10 to the negative 5. So in general, negative power when we move the decimal place to the right, like we did in the examples, and we have a positive power when we move the decimal place to the left, right? So in this example, when we wanted to convert this big number into a smaller, a smaller form, not a smaller number, but a smaller form, we did this, and we moved to the left, and basically have a positive power for the scientific notation format. But right here we did this. This is what we did. We moved right. So our scientific notation will be like this. Negative power, right? So yeah, just keep that in mind. Is there anything with infinite sig figs? Yes, there actually is anything with infinite sig figs, and they are called exact numbers. So an example for this would be you count 10 $1 bills. So you have $10. And you are certain about this. You are certain. This is your exact number. Right? So you have 10 $1 bills. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You are certain you have those dollar bills, right? You won't say you have, I have $10.6 bills. No, because you counted those $10 bills. So you wouldn't say that. You would say, I have exactly 10 $1 bills. You would be sure. You would be sure about this. So we would have infinite sig figs, right? Other examples include, like I mentioned before in lecture, 12 inches in 1 foot. That is exact. There's always going to be exactly 12 inches in a foot. So that is infinite sig figs, right? 2.54 centimeters in 1 inch. Again, generally an accepted value. Infinite sig figs. That is an exact number, an exact amount of how many centimeters are in an inch. And we have 12 in 1 dozen. No one's going to be like, is a dozen 12.1 or 11.9? No one's going to say that. It is 12 in 1 dozen. That is certain. That is an exact number. Infinite sig figs. All these have infinite sig figs, right? So So basically, infinite sig figs, they have no effect on determining sig figs in calculations, which we'll see next lecture when we do calculations with this stuff. So yeah, they have no effect in calculations. Well, sig figs in calculations. So if stated as exact, then it is safe to assume that infinite sig figs when doing these problems. So again, this is gonna be like, this is the lecture. We're gonna go more over this stuff in the next lecture. Yeah, this is gonna be your rough introduction to this. Actually, I hope this is a good introduction. So yeah, that's it. I am going to link, or I'm gonna try and link the notes, a blank notes, well, blank version of the notes in the description. So if you want to follow along, you can download the notes and follow along. So that's it, and good luck.